let's get a little further with this idea that we started. So looking at the vorticity equation for a beta plane with the zonally uniform, so du dx is 0, symmetric, the zonal symmetric flow, then the solutions have this form. Since we are interested in the extratropical signal propagating into the tropics, we are interested in the meridional wave number and the group velocity in the meridional direction, because that is the energy propagation, right? So the condition for oscillatory solution here is that L and M, meridional wave number and the vertical wave number, are real. So that's this condition, which can be read as saying that the zonal phase speed has to be greater than local Rossby phase velocity. So you can move this here and write it as UG minus, so this is, I think, an error, but you can figure it out. So essentially, let's just go to the physics, that the period and wave number determine at what wave number and basic state can the signal propagate equatorward or meridionally. Okay, so longitudinal phase speed cgx equals omega over k as a function of the zonal wave number here, ka, for different values of the basic state. So going from minus 50 meter per second, minus 30, so we are putting in here easterly basic state, and we are changing the period of the wave, and we are trying to see, this is the red line here, is the critical latitude where the wave can escape into the lower latitudes. Okay, so if you have a perturbation that is propagating at wave number, a longish wave number of less than 2, then in a basic state of minus 10 meter per second easterlies, you need a period of 25 days for the wave to get out of the easterly. You remember that the waves were propagating from the equator outward in the westerly duct. Now we are looking at the other way, looking for where the extratropical signal will propagate into the tropics. Okay, so the other example is wave number about 3 can cross over if the period of the wave is 15. So you are matching frequencies and wave numbers, and for short wave scale of minus 8 wave number, minus 8 of k is what? It's basically westward propagating Rossby wave, right? So that's going to cross if the period is 5 days. Okay, we will extend that to look at the phase and group velocities in the vertical and meridional. So if you remember our ray path relations we wrote before in the wave kinematics, dm dt is minus k du bar z dz, and dl dt is minus k du bar y dy. Okay, so let's take a Rossby wave with the Doppler shifted frequency given by this, where the gravity wave speed is given by square root g h bar. H bar is still our mean depth or equivalent depth. Then we can write the meridional group velocity. That's what we are most interested in, because we want to look at energy propagating in the meridional directions from the extratropics to the tropics. That can be written as d omega L dl. So just d omega L dl and omega over k. So we have the phase velocity and the group velocity for the wave, the perturbation. Think about some perturbation in the extratropics that has a waveform could be a Rossby wave that is breaking in the storm track, as we will see, or some other forcing that's placed there that's going to then propagate equatorward. For transporting energy towards the tropics, we want group velocity to be less than 0. In the northern hemisphere it's southward, in the southern hemisphere is y is negative, so it's northward, so you still have CGY less than 0. So that equation, the phase velocity equation, can be solved for L squared, which has this form, and now we have in the denominator, sorry that these things got cut off and I copied it, u bar minus CPX. With the group velocity equation given by this, we can combine these two, and we can now look at the ray path in the zonal direction. Here we had written it for zonally asymmetric case because u bar du bar dx is not 0, but if it is a zonally symmetric case, then this becomes 0. So then the meridional ray path equation, wave number variability with respect to the basic state, can be written as dl dt equals magnitude of k times du bar dy. This is a positive number, so we are just going to look for a zonal perturbation with wave number k that's in a zonally symmetric flow. So then what is its wave number modulation by the meridional shear? Obviously we are headed towards extratropics to tropics, let's say from a westerly regime into a regime that varies along the equator, has easterlies, westerlies and easterlies, as you remember, and we will see in a figure in a minute. So essentially we can determine the impacts of changes in the meridional wave number on the meridional group speed. So we are interested in energy propagation, and we are looking at the wave's interaction with the basic state, which modifies L, which modifies group speed. So that's what we are looking for. So we know that if group speed tends to 0, we know that group speed tends to 0 if L increases as predicted by 911. Okay, which means what? As the wave gets shorter and shorter, we are going to trap the wave, and energy propagation is going to be reduced as well. So group velocity goes to 0. If the meridional shear is greater than 0, so if you are going, let's say, from easterlies to westerlies, irrespective of the value of k, whether the wave is moving eastward or westward, an extratropical mode will not propagate into the tropics if from 912 if the basic state is greater than the phase velocity of the wave. So meridional dispersion of energy is not possible in this case. It's going to be meridionally trapped. Okay, so the same idea as we discussed before. As u bar tends towards CPX, so the phase velocity and the basic state become almost equal, then again the group velocity tends to 0, thus the meridional energy flux should also cease at the critical latitude. Critical latitude is where essentially you have u bar equals CPX. Okay. As the wave approaches a critical latitude, as CPX approaches u bar, then that equation states that L squared must increase. In other words, the wave is getting trapped and getting shorter, which means L is increasing. So the same basic wave kinematics we talked about, we are now putting in terms of the zonal state and the meridional shear. Okay. We'll add complications as we go along, but we will look at this model from walk in a minute. Let me stop the other podcast here. So the equations are complicated, but just understand the physics of the perturbation in the extratropics. that has to propagate meridionally to enter the tropics, and we will see various basic states in which this becomes possible. And typically we always look at these in terms of vorticity equation. We started with the vorticity equation because when you move in the meridional direction, you are changing the planetary vorticity, so the relative vorticity has to change if the total vorticity has to be conserved. Right? That's why it's easier to do that in terms of the vorticity equations and then evolve the solutions.